Welcome to myworldofphysics.co.uk. Today I'm going to talk about the work Localization and Exact Holography that you can find on arXiv. In this paper, we study the ADS-251 holography near the horizon of four-dimensional big black holes in n equals 8 string theory. The ADS-251 correspondence relates the bulk ADS-2 partition function to the number of ground states of the conformal field theory. Using recent results on localization of n equals to supergravity on ADS2 and known BPS state counting formulas, we show that both sides of the correspondence match almost exactly, even for finite charges. To count 1/8 BPS states, we'll look at the 1D5 system on the background of a single closed-decline monopole. The index is extracted by performing a Fourier transform of a weight -2 Jacobi form. Using the modular properties of the Jacobi form, we can write the index in an exact Hadamard expansion. The index is given by an infinite sum over Bessel functions weighted by an algebraic factor called Klustermann sum. For the leading term, the Klustermann sum equals 1. In a large charge limit, we recover the Bekenstein-Hawking entropy, but we can also compute in a systematic way corrections to this result. However, our goal is to determine completely from gravity the Bessel function, even for small charges. Note that in general, index does not equal degeneracy. However, for black holes that preserve at least 4 supercharges, closure of the SUSY algebra implies that it has to be spherically symmetric. Since all the near horizon states carry zero angular momentum, trace of -1 to the power j equals trace of 1. So in fact, index equals degeneracy. This establishes an exact relation between the microscopic BPS states and the number of ground states of the conformal field theory. We are left to compute the expression value of the Wilson line. To go beyond the perturbative computations, we can try to use supersymmetric localization. By deforming the regional action by a Q-exact term, we can compute the partition function in an exact semi-classical computation. We are led to find the saddle point solutions of the localization action and compute the one-loop determinant of fluctuations around them. Usually, this corresponds to solving some BPS equations. In the paper Quantum Black Holes Localization and the Topological String, we applied this technique on n equals 2 off-shell supergravity with a general prepotential. However, for the n equals 8 theory, the prepotential is fairly simple and does not contain information about higher derivative corrections. It is found that the localization equations leave unfixed the vector multiplet scalars at the expense of turning on the auxiliary fields. The renormalized action is computed to have the following form, while the degeneracy is now given by a finite dimensional integral over some fictitious potentials phi, and m is some measure that assures the relative invariance of the answer. To determine this measure, we use usual rules of quantum field theory and normalize the fields using the physical Einstein-Poincare metric. The measure is determined to be of the form. Note that this measure contains additional powers of the Kähler potential, in contrast with other derivations in the context of the OSV conjecture. After a couple of Gaussian integrals, we arrive at the final answer, which is the expected Bessel function of a weight 7/2. The integration variable t is identified with the exponential of the Kähler potential, which is also the conformal factor of the physical metric. It is known that the conformal factor has a wrong sign kinetic term, and therefore it has to be analytically continued to the imaginary axis. This explains the imaginary contour of the Bessel function. Thanks.